Welcome, everyone. Welcome to our webinar, The Washington Sea Level Rise Projections and How to Choose and Use Numbers. Today's webinar is sponsored by the Shoreline and Coastal Planners Group with the support from the Washington Department of Ecology, Climate Impacts Group at the University of Washington, and Washington Sea Grant. The Shoreline Coastal Planners Group is an educational organization of multidisciplinary groups and individuals working for nonprofits, conservation districts, private consultants, and federal, state, and local tribes and local and tribal governments. And it's sponsored by the Washington Sea Grant and the Washington Department of Ecology. And we host workshops and webinars. We provide updates on relevant information for shoreline coastal planners. And we also provide information through our listserv, which we hope, if you're not already on, that you will join. Before we get started today, I want to just go over some of the logistics. This webinar is being recorded, so we will be posting it after today on both the Shoreline Coastal Planner Group website and also the Coastal Hazards Resilience Network website. And the links for those will be provided at the end. And we also will be providing some of those links in the chat box as we go along. The other thing is that we will be taking questions for each of the speakers. You're all muted, and so just be aware that you won't be able to ask questions. If you do have questions, you'll need to put them in the chat box. And we will be monitoring that as we go along throughout the morning. So please feel free to enter your questions, and we'll do our best to answer as many of them as we can. We have this registered also for you planners out there. It is registered for AICP credits. So we're going to post the document, the how to choose document, in the chat box. And also we're posting the link to the Tableau tool that we'll be talking about. We will be, if you can't get access to the tool, to the chat box, we will also be sending that out tomorrow with an email to all of you who participated with a question and answers, asking you to just answer a brief survey. So let's start with introducing ourselves. I'm Nicole Fagan, and I'm a coastal management specialist with Washington Sea Grant, where I help shoreline and coastal planners and managers find solutions for the complex shoreline issues. Babak Telebi is the Senior Coastal Planner for the Washington State Department of Ecology's Shorelands and Environmental Assistance Program. He manages implementation and operation of the state's coastal management program. And he is the lead on coastal policy, community resilience to natural hazards, and climate adaptation planning. Crystal Raymond is a climate adaptation specialist with the Climate Impacts Group at the University of Washington. She's worked on climate adaptation for over 10 years and as both a researcher and a practitioner. And she's currently working on climate adaptation and resilience as it relates to natural systems, coasts, and water resources of the Pacific Northwest. Harriet Morgan is a researcher with the Climate Impacts Group at the University of Washington. Harriet's professional mission is to provide decision makers and natural resource managers with the climate science and information they need to effectively build resilience to climate variability and change. So now I'm going to turn it over to Babak.
Great, thanks, Nicole. Sorry, everybody, for not having my camera on. My internet's been a little bit spotty today. But before we dive into the presentations, I just wanted to provide a few minutes of a little more background and context. So in 2016, a partnership of Washington Sea Grant, the Department of Ecology, the University of Washington Climate Impacts Group, the Nature Conservancy, and a number of key partners from other agencies, universities, and NGOs were selected to receive a 3-year coastal resilience grant from NOAA's Office for Coastal Management. The purpose of this grant was to rapidly increase our state's capacity to prepare for natural hazards that threaten our coasts. Over the next 3.5 to 4 years, we focused on improving our technical knowledge about sea level rise, increasing the state's ability to respond to coastal hazards, identifying and working with pilot communities to test the technical knowledge, and developing more training and education opportunities for everyone in Washington State. This slide shows the products of this work, but I'm sure most of you are familiar with those products so far. So fostering resilience to rising seas requires more than sea level rise projections alone. Coastal decision makers are faced with many questions that the data sets can't answer. After releasing the 2018 report, Sea Level Rise in Washington State, a 2018 assessment, we heard ongoing inquiries from residents, local governments, and other experts about how to use the data. In response, we created a new guide, How to Choose, to help coastal planners, engineers, climate adaptation specialists, and other decision makers understand the various sea level rise data subsets and how to use them to make sound decisions for their particular project and community. This was a difficult document to develop because sea level rise will influence a wide range of decisions that are being made on the coast. We acknowledge that there may not be a definitive answer for how you apply this information in every situation, but our hope is that this will initiate a thoughtful conversation and help you further down the path to creating a more resilient projects and planning. So today we would like to walk you through the guide to demonstrate how to make critical choices when using sea level rise data. The presentations today will include selecting an appropriate time frame, weighing the possibilities of different sea level rise projections against risk, and choosing whether to consider projections that assume a high or low level of future greenhouse gas emissions. I want to thank you again for joining us today in an ongoing effort to protect our state and our resources. Now I'll turn it over to Crystal to get us started.
Great, thank you Bobek and Nicole for that introduction. And as Bobek said, I'm going to be walking you through our How to Choose document that's intended to provide some additional information about how to use the 2018 sea level rise projections that were developed as part of the Washington Coastal Resilience Project. And it's great to see so much interest in this topic, and we hope that we will be able to give you a good sense of how to use these numbers with this document. Just a moment here waiting for my slides to catch up. Great, there we go. And so I'm going to start by giving a brief summary of the 2018 projections and how they differ from sea level rise projections that we've had for this region in the past. These 2018 projections include the latest information on sea level rise research. Go back here one slide. You'll have to bear with me. There's a bit of a delay in advancing the slides. Well, maybe I'll skip through that slide. So the key differences in the 2018 projections are that they are based on the latest sea level rise science. They are local in that they include vertical land movement along Washington's coast. So this gives the variation in the projections at the local scale based on areas of the coast that are uplifting or subsiding. And the third key difference is that these sea level rise projections are probabilistic. That means we have associated probabilities with each of the values within the range of the projections. So this is significant new information included in these projections. And with that comes a need to make some very conscious decisions about which numbers are used and how to choose those numbers for different situations. So the How to Choose document includes 4 different decision points, and I'm going to walk through the processes of making these decisions. The location that you use, which time frame you use, which probabilities of sea level rise you select, and for which greenhouse gas scenarios. And one of the key points that I want to make here is that science has given us these sea level rise projections. They were developed as part of the Washington Coastal Resilience Project. And the science is really in the numbers and the range of projections that are given. But in terms of which numbers you choose to use from that range is not a scientific question. Science can't answer that. It's really a question about your organization, the risk tolerance of your organization, and what is appropriate for a given situation. And so what we are intending to do with this document is guide you to the right questions to ask when deciding which numbers are right to use for your application. The document is also organized around 4 different potential uses of the sea level rise values. And these are certainly not exhaustive. There could be other uses as well, but these are common ones that we've come across in helping people to use these numbers over the last couple of years. So some people are interested in using them for vulnerability assessments and resilience plans or risk assessments. Other people may use them in planning, such as comprehensive plans or plans for the Shoreline Master Program. They can be used in very specific project design, such as design of infrastructure, or in nearshore restoration projects as well. And the decisions that need to be made in terms of choosing which numbers to use are similar for all these applications, but there's different factors that you might consider depending on which use you are interested in or working on. We also want to acknowledge that potentially all these uses may be going on in one organization at the same time. And I also want to just briefly talk about what you do with the numbers once you select them before I jump into each of the decisions. So these sea level rise values are the expected change in average sea level. This is change relative to the 1991 to 2009 mean. And they can be used to evaluate the future change in any current water level. So a common use of them is to apply these change values to the current mean higher high water value. And that gives you what would be the future mean higher high water with sea level rise. It doesn't have to be mean higher high water. There may be cases where mean lower low water is more of interest, particularly looking at lower intertidal habitats or navigation applications. So really they're flexible in their use in that they're not tied to any specific current water level. The other thing I want to do throughout this presentation is to point you to the other documents as part of the Washington Coastal Resilience Project, because they can provide additional information on any of these topics if you'd like to follow up with more detail. So what I'm describing here is described in more detail in the guidelines for mapping sea level rise and inundation. And to show you what this looks like in a coastal profile, so here would be our current water levels. We have mean sea level. Below that, you have the mean lower low water and the mean higher high water. So that is the daily average high tide for a particular location under current conditions. And then if you're interested in that future mean higher high water, you can simply take the sea level rise values that you choose. In this case, we're looking at 2 feet, and add that to the mean higher high water. And now you have your new future higher high water. We also recognize that many people are interested in water levels that are more extreme than the mean higher high water. So higher water levels that occur less frequently due to storm surge or waves. And these values can be used in combination with that information as well. So there is another document in our series, Extreme Coastal Water Levels in Washington State, which provides some information on what these more extreme coastal water levels are around the state and how to combine the sea level rise information with that. So an important consideration when using these is what water level are you concerned about for your application? So are you interested in that daily average high tide? So the area that would be inundated on average once a day, or are you interested in something that is less frequent but a higher water level, such as a 10-year coastal flood or the FEMA 100-year flood level? And just as we did with mean higher high water, you can add these sea level rise projections to those more extreme water levels. For example, the current FEMA 100-year base flood includes the storm surge and waves in most area. And by adding sea level rise to that, you're getting what that 100-year flood would be in the future. The current modeling of the 100-year flood does not include any sea level rise information. So now I want to walk you through the decisions that need to be made when selecting numbers, and these follow the decisions that are included in our document. So as I said, the projections are local. There's 171 segments along Washington's coast. The size of those segments varies just because of the irregular coastline. And the projections of sea level rise themselves differ among the segments simply because of that vertical land movement. So in places where you have subsidence, there will be a higher rate of sea level rise. In places where there's uplift, there'll be lower rates of sea level rise. And there's a few options for selecting locations depending on your application. If you are looking at project design or a nearshore restoration project in a specific site, you can simply select that single location and use those values. There may be situations where a planning or a policy situation where you want to be looking at the projections for a larger area, such as the coast of an island or a county. In that case, you have a couple of options. You can select a representative location, and a Tableau visualization tool that we have for viewing the data will allow you to look at different projections in your area and identify what a representative location would be. You also have the option of looking at multiple and averaging multiple projections for your area of interest, and you can download the data from the Tableau visualization tool and simply average the values for multiple locations. One comment, though, that I want to make about that is that these projections are intended to be local by picking up that fine scale variation in vertical land movement along the coast. And so in areas along the coast, such as the ones that I've circled here, there's a very steep gradient, a lot of variation in that vertical land movement over a short area. And so in these cases, it would not make sense to average multiple points along the coast, because that would result in values that aren't necessarily meaningful and average out that local variation. The next decision that needs to be made is about the time frame. So unlike previous projections that typically gave a value for simply 2050 or 2100, the 2018 sea level rise projections provide values for every decade between 2010 and 2150. These decades are actually the average of a 19-year period centered on the decade. So for example, 2070 would be the average sea level rise for 2061 to 2079. And when you download the data from the website, you can see all these decades and select whichever one is most appropriate for your application. So this increases the flexibility of the data and allows you to really select a time frame that's specific to how you want to use the information. There's a couple of different things to consider when you're trying to decide on a time frame, and this really varies by your application. If you're looking at vulnerability or risk assessments, it makes most sense to select multiple timeframes and compare how the risk associated with sea level rise would change over time as part of that assessment process. If you're using an application of policies and plans, then you can take into consideration the time frame of that plan. Is it intended for 20 years, 50 years? But also consider what that plan affects. If it affects coastal development, are you looking at coastal development that may actually last much longer into the future besides the time frame of the plan itself, in which case you would want to look at a longer time frame. Another important consideration is potential updates and revisions. How often can your plan be revised or updated? If it's a fairly frequent revision schedule, then using more near-term timeframes may be appropriate. If it's difficult to revise a plan or update it in the future, then you might want to consider longer timeframes. Project design is probably the most straightforward situation in selecting a time frame. In this case, often infrastructure has a designated design life, and that can be a good indicator of the time frame you would want to use. So for example, if you're building a road with an 80-year life expectancy, then selecting projections for 2100 would be appropriate. One of the things that we have come across in this process is that learning that the specified design lives of infrastructure often differ from the actual design life, where in some cases you may have infrastructure that is upgraded more frequently because of technology and therefore has a shorter design life in reality, and you could use more near-term projections for that. Whereas we also hear the opposite is often true, where infrastructure is maintained to last much longer than its design life just because of funding and the ability to upgrade. And so in that case, you might want to be thinking about an even longer time frame. And for nearshore restoration projects, there can be a variety of different goals, and different timeframes would be relevant. There can be near-term, short-term habitat goals, and short-term projections would be appropriate for that. On the other hand, if the focus is really restoring ecological processes for the long term, then long-term projections 2100, 2150 may be more appropriate. And we've also heard that for restoration projects that are focused on processes, the rate of sea level rise can be particularly important. And the rate is not included in the values directly, but it can be easily calculated from the data if you want to look at the rate of sea level rise relative to other processes like marsh accretion. And the third decision is about probabilities. So these projections include a full range of probabilities from 99% to 0.1%. At the high end of the probabilities, 99% to 83%, these are low values of sea level rise. And these values are very likely to be exceeded in the future. On the other end of that range, we have the 17% to 1%, which are very low probabilities, high values of sea level rise, and these are less likely to be exceeded. In the middle of that range, we have what we call the likely range, which we have designated as the 83 to 17% probability. And in the very middle, of course, is the 50%, which is the most likely value. So with 50%, that means that sea level rise is just as likely to be above that value as not. So for example, in this graph here, you see that the 50% value in 2100 is 2 feet. So that means sea level rise in 2100 is just as likely to be above 2 feet as below. And at the very low end of the probabilities, we have the 0.1% probability. This is an extreme low probability that's intended to be a physical upper bound to what sea level rise projections could be in the future. And the idea with this is simply that even with additional research on sea level rise, this upper bound is unlikely to be revised in the future. And the intention of these probabilities is that they can relate very directly to risk management and thinking about managing your risk for sea level rise. So if we go again to those high probability values, the low amounts of sea level rise, these are really most appropriate to risk tolerant situations. So applications in which your project can tolerate sea level rise being greater than the values for which you plan, because these are likely to be exceeded. On the other end, the 17 to 1% probability, these are for risk-averse situations, so applications that really cannot tolerate sea level rise being greater than the values that you plan for, and this is a fairly conservative part of the range to use. So for example, this might be in the application of a wastewater treatment plant. On the other end, on the risk tolerant side, appropriate applications for that might be things like a parking lot, a picnic area, a campground, or infrastructure that can tolerate some sea level rise. And then in the middle again, with moderate risk, is the 17 to 83% probability. And so our fourth and final decision is about the greenhouse gas scenario. So that probability range that I described is available for each of 2 greenhouse gas scenarios. So these greenhouse gas scenarios are essentially different futures associated with climate change based on different assumptions about population growth and emissions. The key information to know for this is that the RCP 8.5 greenhouse gas scenario is for more warming and therefore a higher rate of sea level rise that reaches a higher value by 2150, compared to RCP 4.5, which is a lower greenhouse gas scenario and therefore has lower warming and a lower rate of sea level rise through the century. One of the critical things, as you can see from this graph, is that the sea level rise projections for these two greenhouse gas scenarios do not differ until about 2050. So if you're using a time frame and selecting numbers for your application prior to 2050, it doesn't necessarily matter which greenhouse gas scenario you choose because they're essentially the same. If you're looking at timeframes beyond 2150, then it's important to consider which of these greenhouse gas scenarios you would like to use. Some considerations for that, for example, again, for vulnerability assessments or risk assessments, the most appropriate thing is probably to compare both greenhouse gas scenarios and sea level rise values for those to see what the different impacts may be and determine to what extent it makes a difference, depending on which one you use. Another important consideration, particularly in policy and planning, is consistency with climate change information that may be used throughout your organization elsewhere. So these greenhouse gas scenarios are not only used in a sea level rise context, they're used for other climate change projections that may relate to terrestrial systems or water resources. And so one of the things you may want to consider there is consistency throughout your organization as to what other greenhouse gas scenarios are used. And so, I just want to say again as a reminder that these decisions are really institutional decisions that are based on your institution's risk tolerance and what may be appropriate for the context in which you're using the values. And that really requires some internal discussions within an organization in terms of making those decisions. And so I just want to close by saying that the choosing values to use for your sea level rise application is really actually probably the first step in the process. There certainly needs to be some outreach and engagement around those values. We've heard that in many cases where people are applying these, that the public it may be appropriate to give the public an opportunity to weigh in on which values you're using and why. And then of course, the most important next step is what do you do differently based on those sea level rise values that you've selected. So for example, if you're using them in a project design application, how is that project going to be designed differently? How would you design a nearshore restoration project differently based on the sea level rise values that you've choose? And these projections were updated in 2018, as I said, and we know that the science around sea level rise is evolving and likely new science will change the projections in the future. Given that we have this wide range, we wouldn't necessarily expect the range of projections to change, but the probabilities associated with values within that range may change. And so part of your process in using these values is to think about how you might revisit them in the future and build that flexibility and opportunities for updates within your applications for the information. And that is what I have, and I believe at this point I can take some questions.
Does anybody have anything that they want to put in the chat box to let us know that you want clarification on anything Crystal talked about? I'll start you off by, Crystal, I'm going to ask, can you give some examples of, with vulnerability assessments, how do you use this kind of information? Because I would imagine you need to think about multiple time frames. Can you give an example of how that might be used?
Yeah, so for vulnerability assessment applications, I would recommend looking at multiple timeframes so that you see how the level of sea level rise, how sea level rise changes over time, and then that allows you to see what infrastructure within your assessment area may be affected over time. So a critical step in vulnerability assessments is to map the sea level rise information, and then that allows you to see which infrastructure would be affected at what point in the future. And obviously that can also interact with the probabilities. So in an assessment context, in addition to choosing multiple timeframes, you can choose multiple probabilities. And then that gives you a sense of what might be the risks that you're concerned about that you would want to develop specific actions in response to. And so vulnerability assessments are really an opportunity to explore the impacts. And then when it comes to actually making a decision about doing something differently, you may have to move to more specific numbers, choosing one or a few numbers in order to develop a policy or design things differently. But that assessment opportunity is really a chance to explore what the impacts might be of different probabilities and different timeframes.
And then how would that compare to when you might use different time frames? So that's the different probabilities. So why would you want to use different time frames?
So different timeframes would simply be to see how sea level rise impacts your area of interest over time. So it would give you a sense of if there's a need to act now, if you see that there are significant impacts to infrastructure you care about within 20, 30-year time frame, then that may motivate change. If you take a look at a range of timeframes and you see that really there aren't any impacts in your area until 2100, then that suggests that you have some time and there may not be need to take action right away. So really seeing when impacts emerge for your region or the area that you care about allows you to decide when you need to act.
Question for you is how can you talk about this is about how to use the numbers, but there is some question about how we develop them, and then what are the sources of uncertainty that lead to the need for creating this probabilistic approach?
Yes, that's a great question. And so those documents that we showed that Bob Eck presented provide a lot of background on the uncertainty. And so the probability range was developed specifically to account for that range of uncertainty. And so I can refer you to those documents to see additional sources of uncertainty, but it includes all the different factors, the physical factors that contribute to sea level rise. So the thermal expansion of the ocean, the melting of the ice sheets, Greenland and Antarctica ice. And so all those factors are included to develop that probability range using the Kopp et al. Process of developing that. And so we've included those there. And then because you can't assign probabilities to the greenhouse gas scenarios themselves, we have developed the probabilities separately for the two greenhouse gas scenarios. So the greenhouse gas scenarios are essentially another source of uncertainty in that we don't know exactly what the future will be for greenhouse gas scenarios. And one of the ways to account for that uncertainty is by having two different probability ranges, and then you can select from those depending on which you want to use.
This document, like you said, there's a whole suite of documents that have been prepared, and this document in particular is diving in how do we actually use probability, the projections that were created in 2018. There's a couple of questions that people have asked more about the projections themselves, and so I'm going to put them out there, but I just want to let people also know that there is that a lot of the information and about the science tends to be related to it's in the research that was done as part of developing the projections. But the question was, have travel patterns from COVID added any new data to adjust sea level rise rates? It's still relatively new, but it seems as if greenhouse gases have been reduced. Do you want to talk at all about that?
You know, I think it will be very fascinating, I think, to see the extent to which the change in travel patterns makes a difference in greenhouse gas scenarios. There's a major study in progress right now, or an experiment, I should say, an experiment in process right now, which I'm really interested in to see. Certainly too early to tell. I think, unfortunately, it's probably a small blip in our greenhouse gas emissions. And one of the critical things about sea level rise relative to some of the other climate impacts is that there is a really big lag in the warming associated with greenhouse gas scenarios and what you actually see for sea level rise. So also, you know, this being one small period of time where we reduce emissions and taking in consideration the lag with sea level rise, I think we probably would not see a very big impact, but I am sure that that will be forthcoming research that we will see at some point, and it's just too early to tell now.
Mm-hmm. With science saying that we're observing what's happening in the Arctic now, that the projected to what was happening in 2100, what do you think we're going to see in changes to probabilities between now and 2100?
Yeah, I couldn't speculate on this, so I don't want to delve too deep into it because I was not involved in developing the probabilities themselves. I will say that part of having that 0.1% probability was to really have an upper physical bound. And so, as I said, yeah, the probabilities may shift. But at this point, I think I would just be speculating to say what those are. But yes, the research coming out of the Arctic and other places is really changing rapidly. And so I think that's a reason that we need to be aware that these probabilities could be revised in the future. I hesitate to say that because I think it sometimes causes people to think that we don't know enough to use these values or to make a change. But I think that can be an excuse, and I think really more what it points to is the need to build in flexibility, to look at a range of values, to build flexibility into updates to your plans or how you might use the values, and to come back and revisit them to the extent that you can, to build adaptability into flexibility into projects. And actually, I can give you maybe kind of one good example of that from the proposed sea level rise risk zone for King County. They've actually used the sea level rise values and tied those directly to the FEMA 100-year base flood elevation. And so in a way, that's a way of building in the flexibility. So as sea level emerges over time and that FEMA 100-year floodplain changes and becomes remodeled, then the sea level rise values are just added on to the top of that. And so that is really a way to build in flexibility so that as these probabilities and numbers get revised in the future, what you've planned for is also moving along with that development.
Another good question that I wanted to have you address, and this was somebody asking and specifically about the Duwamish, but I think it's relevant to everything and making clarifications about what is being addressed with these sea level rise projections is talking about when you talk about compounding flooding impacts from sea level rise, storm surge and river flooding, groundwater, soil saturation, does this data consider those impacts?
So the values are changes in average sea level that are not tied to any particular current water level. So if you're interested in storm surge or wave run up or have a particular water level in the current situation that you're interested in seeing how that will change to the future, you can simply add these sea level rise values to it. In terms of changes in storm surge or wave run up itself, that is not included. And the current science indicates that we would not expect the storm surge or wave run up itself to change with sea level rise. It's just that that is higher up on the land due to the underlying change in sea level. But that is an active area of research and one that requires more of a hydrodynamic modeling, which is in progress around the region, but is not currently included in these values. So in using them as sort of this bathtub approach where we just have the base level moving up, you're really assuming that the storm surge and high flooding dynamics do not change themselves. In terms of groundwater or other potential sea level rise impacts, we acknowledge that those are very important factors to consider in project and planning contexts. And these data themselves do not address that directly, but they can certainly be used for additional modeling or assessment studies that could look at how higher levels of sea level rise might affect something like saltwater intrusion into groundwater, other factors that you care about. So these are really the starting point to do additional assessments to look at those issues.
Thanks, Crystal. One more question that came up that I'm going to use as our transition point here is there online resource for walking through these considerations? And it was a very well-poised question because our next speaker is Harriet Morgan. And I'm going to turn it over to Harriet, who is going to speak about the use of a tool called the Tableau.
Great, thanks, Nicole. So yeah, today I'm going to be talking about and doing a walkthrough of a tool that we developed in partnership with Tableau software to visualize the 2018 sea level rise projections for Washington State. A link has just been provided to you in the chat window, so you can go and explore and sort of do a walk along with me here. Okay, so before I get into the nitty gritty of kind of walking through this visualization, oops, go back. See if I can go back. Just give me a minute. Got a little bit of a lag with the slide advancing here. There we go. Okay, so before doing a full live walkthrough of the visualization, we're going to take a step back and talk briefly about our starting point with these sea level rise projections and what really motivated the development of the Tableau viz. So the screen you are seeing here is kind of the before. So previous to this Tableau visualization, in order to access the sea level rise projections for your area of interest, you would zoom in on this Google map and click on the blue circle that's closest to your area of interest or your site. Once you click on one of these blue circles, you'd be prompted with an Excel workbook that would download for this area. And each Excel workbook contained 2 Excel spreadsheets. So we have this spreadsheet that would download, which is the sea level rise projections that were generated under this low greenhouse gas scenario. And then you would also get another spreadsheet that was the sea level rise projections generated under a high greenhouse gas scenario. And so we have these spreadsheets for each of the 171 sites along Washington's coastline. And at the end of the day, that ended up being a lot of spreadsheets. And we found out very quickly that people do not love Excel spreadsheets. And there were 3 primary challenges with the spreadsheet. The first being that they're static. It was very hard for users to visualize change in sea level rise through the 21st century and beyond by just looking at static spreadsheets. The second challenge was that the spreadsheets really don't facilitate comparison between the 2 greenhouse gas scenarios easily. You kind of had to line them up on your desktop and toggle back and forth, which was challenging. And finally, there was no real clear takeaway message from the spreadsheets. If you wanted to get like a high level takeaway message for your site or for your project area, you really had to spend a lot of time with these spreadsheets and kind of wade through the data. And so the reason I highlight these challenges with the spreadsheets is those 3 factors are kind of what we wanted to achieve with the Tableau sea level rise visualization. So the tool that we produce actually ended up developing 2 different ways to visualize the Washington State 2018 relative sea level rise projections. And both visualizations allow users to explore how the projections change through the time period considered, which is from 2020 out to 2150, for all of those 171 locations along Washington's coastline, as well as considering 2 different greenhouse gas scenarios. So here's a screen grab of visualization 1. I'm going to be doing a live walkthrough, so we're going to get into all the nitty-gritty details of this. But as a high level sort of starting point, this visualization essentially allows you to explore different likelihoods for how much sea level rise could occur at different points in time. So an example question that you might present when using this visualization would be, how likely is it that we will see 1 foot of sea level rise by 2050 at this specific location that we've selected? So that's visualization 1. If we click, we'll go to a screen grab of visualization 2. So this is slicing the data in a slightly different way. So visualization 2 allows users to explore the likelihood of a given sea level change by a specific year. So we would be using visualization 2 to answer a kind of question like, when are we expected to see 1.5 feet of sea level rise at this location? Okay, so that's kind of my presentation bit, and now I'm gonna stop my sharing and transition over to our live walkthrough here. So let me minimize this and share that. Okay. So now you guys should be able to see my internet browser here. Here we're on the Climate Impacts Group website. If we scroll down, we get to visualization 1. This is basically the same thing of the screen grab I was just showing you. So our first task here is to select our location of interest. So you choose a location of interest within this Tableau viz by clicking on a blue line segment. So if you hover your cursor over these line segments, you'll notice that they're kind of popping out and highlighting. So each of these are a separate set of sea level rise projections. And we've built in a variety of different ways that enable you to navigate to your location of interest. So for example, we have the search toolbar up here where you can search for towns, cities, as well as zip codes. You can also use a more traditional panning feature where you can zoom in and out by double clicking using your scroll bar and your mouse and dragging around. And we've also built in these sort of preset filters. So if you're interested in a specific county and you want to see all the line segments within a county, you just select that drop down. I'll reset it quickly here, and it'll bring you to all of the line segments within that county. In addition to the county filter, we've also built in this water resource inventory area filter in case that is the geographic scale at which you are planning for sea level rise. And there's a variety of options here as well. So for the sake of this example, I'm going to say that we're interested in looking at Olympia. So we'll throw in Olympia in our search bar, and then we select a specific line segment that we're interested in. When we click on it, we'll notice that our projections populate here on the right. So we've selected a location. Our next step that we need to do is select our likelihoods or our probabilities of exceedance. Again, this is the likelihood that sea level rise is going to meet or exceed a particular magnitude of sea level rise by a point in the future. So I want to emphasize that when we're selecting a probability of exceedance, the most important factor to understand is the level of risk that's associated with each likelihood here. And the decision of what likelihood you're going to check and explore is going to be an institutional decision. There's no quote unquote right answer here. It's going to depend on a variety of political, financial, and logistical factors that are going to be specific to each organization or decision that you're trying to make. That being said, we do present a variety of likelihoods that we can consider. So we have low probability of exceedance, which kind of range from this 1% to the 17%. These are low probability projections. These magnitudes of sea level rise are less likely to be exceeded. So I like to remember it as low likelihood, lower risk tolerance. So these are appropriate for risk adverse situations. In contrast, we can also look at high probabilities of exceedance. So these would be like from the 83rd percent all the way down to the 99th% probability of exceedance or likelihood. These are high probability probabilities of exceedance. These sea level rise magnitudes are likely to be exceeded. And so it's the shorthand I remember it with is high likelihood, higher risk tolerance. So if you're planning for these likelihoods or probabilities of exceedance, this is kind of a risk tolerant application. You're okay with flooding or sea level rise meeting or exceeding those values. When I'm exploring a site, I typically like to look at the 83rd percent probability of exceedance, the 17, we'll check there, the 50%, and the 1%. So now we've selected our likelihoods. So that was our second decision point. Now we need to move on to our greenhouse gas scenario selections. So the visualization shows relative sea level rise projections for 2 different greenhouse gas scenarios that are known as these representative concentration pathways. So right now we have both selected. If we look at our graph on the right, the high greenhouse gas scenario projections are shown in these shades of orange, and our low greenhouse gas scenario projections are shown in shades of blue. I find when you have both with multiple likelihoods selected, it gets a bit like a plate of spaghetti. So for the sake of simplicity, we're just going to look at the high greenhouse gas scenario for now. Okay, our final sort of customization feature that we have on this visualization is over here on the right. So here we have this slider bar that allows us to select the end year of the projection. So right now it's sort of maxed out at the year 2150. But if we're more interested in 2100, we just drag that slider bar to the left and our graph modifies itself accordingly. If you are interested in designing for the year 2070, you don't necessarily need to drag this to 2070, as you can still see this time frame on your graph. Okay, so those are all of the decisions you pretty much need to make before really diving into the visualizations. So now we can see our visualization is basically divvied up into 2 sections. At the top here, we're looking at projected change in relative sea level rise for our location of interest down in Olympia. On our y-axis, we're looking at projected relative sea level change. This is in feet. And on our x-axis, we're looking at time. So because I've maxed us out at 2100, we're looking at sort of decadal time stamps through the end of the 21st century. And then our legend is showing all of the different likelihood curves that we've selected over here on the left. So our bottom one is our 83% probability of exceedance. We have our 50% probability of exceedance, our 17%, and our 1% probability of exceedance. These lines would change depending on what we select over here on the left side of the visualization. And also notice that we have this data table down here on the bottom. So this is showing the exact same data that's being presented in this line graph. It's just showing it in more of a tabular form. So we have our time column here on the left. We have our different probabilities of exceedance columns or likelihoods. And the various numbers in these cells here are just magnitudes of sea level rise in feet. So my favorite feature of this visualization is what we call this hover function. So if you take your cursor and you hover it over a data point in this line graph, it'll give you this little word box that pops up. This is what we refer to as a tooltip. And it essentially provides you with a very high level takeaway sentence for this data point. So I'll read a few examples. So for example, under the high greenhouse gas scenario, there is a 17% chance that the amount of relative sea level rise will meet or exceed 3.4 feet by 2100 at this location. And you may also notice, I can't show you with my cursor, but if you look down to that data table on the bottom, we're highlighting the year 2100, our 17% probability of exceedance, and we see that 3.4 feet, the cell that's containing that number is highlighted. So it's just showing us where in the data table we are. And the numbers within this tooltip change depending on what curve, what year, and what curve and what year you're looking at. If you prefer to look at the data table, you can do the same thing. Hover your cursor over a cell. It'll give you that tooltip sentence, and will also highlight the corresponding data point in that line graph above. So that's a high-level walkthrough of how visualization number 1 works. Now, if we scroll down on this web page, we'll get to visualization number 2. So notice that we have the same general layout as we did in visualization number 1. However, the big difference here is that rather than selecting likelihoods or probabilities of exceedance, we have the ability to customize different magnitudes of sea level rise in half-foot and 1-foot increments. So for this visualization, we're exploring the likelihood of a certain amount of sea level rise by a specific point in time or through time. So again, our first task is going to be to select our area of interest. So I'm going to use the same location again, just for consistency. So let's go down to Olympia. got to click on our line segment. And once we do that, we're going to populate our graph and our data table here. So for an example, let's say we're thinking of designing for 1.5 feet of sea level rise, or planning for 1.5 feet of sea level rise at our site. And we're curious to find out how likely it is that we're going to see 1.5 feet of sea level rise or more at this particular location through time. So since our example is looking at 1.5 feet, we want to select 1.5 feet. You can add as many of these magnitudes as you want, but for cleanness and simplicity, I'm going to just do 1. So that's our decision there. Our second point we need to work down to is, again, this greenhouse gas scenario option. Since we only looked at the high greenhouse gas scenario last time, let's look at both. And now let's talk a little bit about these graphs and data tables on the right. So you'll notice that even though the layout is the same, the kind of shape of these curves is a little bit different. And the reason for that is because over here on our y-axis, we're now looking at the likelihood of seeing 1.5 feet of sea level rise, because that's what we checked over here on the left, through time, out through the year 2150. Again, you can modify that end year by using the slider bar over here on the right. And so these curves are showing the likelihood of us seeing 1.5 feet of sea level rise through the year 2150. Our two curves are because we've selected both a high and a low greenhouse gas scenario. So the red curve corresponds to the high greenhouse gas scenario, and the low curve corresponds to the low, or excuse me, the blue curve corresponds to the low greenhouse gas scenario. So that we see that for the first few decades, right, up to approximately 2050, there's essentially a 0% chance that we're going to see 1.5 feet of sea level rise. But as we move towards the second half, through the second half of the 21st century, the likelihood of seeing or exceeding that magnitude of 1.5 feet increases. And that's noted here in this tooltip. So let's go out to 2100 and compare. So under the low greenhouse gas scenario, we're looking at the blue curve now, there is an 85% chance that the amount of relative sea level rise will meet or exceed 1.5 feet by 2100. If we contrast that with the high greenhouse gas scenario, see there's a 90% chance that the amount of sea level rise will meet or exceed 1.5 feet by 2100 at this location. And as we move out towards 2150, the likelihood of reaching or exceeding that magnitude only increases. This is very easy to visualize down here on the data table, which again is showing that same data just in tabular form. And you can see again, if you highlight over a cell, it shows in the line graph above the corresponding points that we're looking at. So here in this data table, rather than looking at feet of sea level rise, we're looking at the likelihood of seeing 1.5 feet of sea level rise under different greenhouse gas scenarios. And so that is how visualization 2 works. The last thing I want to talk to you about is the various download features that we have for these different dashboards. So if you click this button in the middle down here, you have the option to download this whole, what we call a dashboard essentially. And this can be used to capture a summary of the data for your site that you can include in reports, send colleagues or clients, etc. You can also download the specific data that you've selected with our customization options. You can download this as a PDF. You can download a customizable PowerPoint slide. So there's a lot of different download options and customization features with this button here. Additionally, if you are very sad that we took away the spreadsheets, fear not, because we actually kept them. So you can download the full Excel spreadsheets, which is both worksheets for this specific location that we've selected here by just clicking on this little box. And so that will allow you to download all data for this site. It's not going to have any of the customization features that I talked about earlier, but it'll give you the entire data set. Thank you. I think I have time to take questions now as well.
Anybody have any questions about the tool? Thank you, Harriet. That really is great, and it's a wonderful tool to be able to use. And we hope you all go ahead and use it. And if you're not already sitting there trying it out, please go ahead and do that. Okay, I'm going to give it a minute and see if there's any questions, and then we'll move on. Okay, good. Well, we're just here to provide you with resources. I'd like to give a case study using an example at Owen Beach in Tacoma to explain how one project used the how to choose and also how our visualization tool can be of assistance. And in this is being able to show you how there are decisions that need to be made that are either project by project or need to be made at a county, city, governmental, tribal level about what information you want to be using for sea level rise and to use these projections that we're talking about. So this comes from Owen Beach Park in Tacoma. And in this case, in 2017, Metro Parks Tacoma approached our resilience team and told us about their project that they had and how they wanted to consider, they were at the point of wanting to consider sea level rise in the planning process that they were doing for it. It's a very popular beach for this community, summer and winter, all year round really, but it was starting to experience some serious erosion impacts and flooding. For example, on this green lawn area, and there's buildings and infrastructure, the parking lot would flood from stormwater runoff, etc. And so Metro Parks had received a grant to restore and build a park, the park. And they'd gotten to, this was a 30% design. So they got to the 30% design and reached out to us and said, we'd like to talk through the project and sea level rise implications. So we had an initial meeting with the designers in Metro Park, talking through both what was existing and then also what they were proposing. We talked about the different aspects of the facility and the anticipated lifespan of the different structures, as well as the level of risk for various aspects of the site. And for example, thinking about structures and risk, they were looking at some of these existing structures and the restrooms and the shelters and parking, and thinking about that level of risk was maybe different from the park and the shoreline and the promenade. So we posed questions to the team about the site that related to sea level rise. We said, let's think about what's the vulnerability of the site and the various aspects of the site. How is it vulnerable? What is it experiencing now? What's the probability then of sea level rise occurring, looking to the work that we were doing? Then let's talk about and think about what's the risk of failure, of underestimating, of there being sea level rise and being impacts from sea level rise at some point in the future. And then how do you determine what year you want to plan for, and then starting to do some cost benefit analysis. What's the costs of planning for these different sea level rises, the different sea level rise, and then how do you balance your risk with some of this cost for design? So some of the issues that came out of these discussions were that they had decided that they needed to think about a 50-year time frame for buildings. Meanwhile, the promenade only really needed a 25-year time span at the most. So thinking about lifespan and time frame for repair, replacement, future work. Overall, though, Metro Park made their own decision that they said, we want to be thinking about sea level rise and we want to be planning for our facilities to withstand a 75-year time frame. And so in that case, they said, we want to think about how do we plan for the year 2090. So I'm going to demonstrate how they use this sea level rise visualization tool and to make these decisions. that they were thinking about. First, they wanted to talk about, they had to make a baseline decision. Do you want to use a high level or low level greenhouse gas projection? In this case, they decided they were going to use high level, or in their way of speaking, it was business as usual. We're assuming that greenhouse gas projections are not going to be changing dramatically and lowering. Next, they decided they wanted to look at the year 2090. And next, they decided to compare different likelihoods. So starting with the 99%, 50%, 17%, and the 1% likelihood. So that's what you see here on the graph. And so what came out of this then is they decided that they wanted to be cautious. In this case, they were saying 20%, although the chart is 17%, so close enough. So they're using the 17, their level of comfort was wanting to think about the 17%. They wanted to be pretty sure that by 2090, they had the right information and they were using that. And so they selected the 17%, which equated with a 2.5 feet of sea level rise by 2090. So this is how they then did the math, trying to figure out how do they show this on the drawings and begin to see what the implications were. So they started with, in this case, 5.85 feet was mean high water on their existing drawings. They added then to that the sea level rise projections, and in this case, what they had selected was the 2.5 feet. Then they also wanted to add then to that the storm surge. In this case, we had not produced our information yet about extreme water levels, so they were using FEMA flood information that gave them this amount of sea level of storm surge of 3.6 feet. So what you come up with then is just doing the math. We're going to look at an aggregate sea elevation for a storm event in the year 2090 of 11.94 feet. This is what it looks like then on a drawing. So go back to the original drawing, and the pink line you see shows where that line of the aggregate sea level rise plus storm surge at 11.94 feet looks like on this 30% drawing that they had produced. And what they could see was that their new restroom and new shelter were really exposed. As well, they saw that the green area that they had created, the park area, potentially was going to be inundated yet again. So they said with this new information, they would go back to the drawing board and see revise their drawings accordingly. So this is the new revised drawing that they came up with. And as again, you can see the 11.94 feet, and you can see how the buildings now are pulled way back. The green area is also pulled back. And then also they've created for the storm water, they've created detention right at the end of the parking area because they were having so much flooding, and to address all of that. So overall, this is a demonstration of a project that has started one way, but taking a step back and starting to think about the lifespan of various facilities and how that's going to be impacted by sea level rise. What are the locations for those facilities? What's time frames, and when you actually start to look at the sea level rise projections, how that really can play a significant role in your design and then your redesign of a project. I'm going to now turn it over to Babak, and he's going to talk about some of the resources that are available. Some of them we've talked about, but also where to look for this information to help you work through some of these kinds of projects.
Great, thanks, Nicole. It's really amazing to see the gathering of information and understanding the sea level rise projections, looking at a tool, interacting with a tool, and then also seeing how that information is applied on the ground to a specific project. So thank you again to you three for presenting. And I just want to close us out here with a little bit more information on where to find all this information and the resources. So what we've heard several years ago and continuing on is, can we have a central location for all the coastal hazards information and resources? So as part of the Washington Coastal Resilience Project, we recently updated the Coastal Hazards Resilience Network website. The goal of the Coastal Hazards Resilience Network is to strengthen the resilience of Washington coastal communities through collaboration, education, and knowledge exchange. The Coastal Hazards Resilience Network increases our members' collective capacity by working together toward a common mission. The network's website will orient you to relevant science, best practices, and other resources related to coastal hazards, including flooding, sea level rise, erosion, landslides, earthquakes, and tsunamis. The membership has over 100 coastal hazards and climate change practitioners from federal, local, and state government agencies, tribes, academic institutions, consulting firms, and nonprofit organizations. The network was established in 2013, and the website is co-managed by the State Department of Ecology and Washington Sea Grant. So I don't have a lot of time to walk you through what this website includes, but all the resources that have been presented on today, including and much more, is all located on the Coastal Hazards Resilience Network website. So I encourage all of you who joined today to join our community of practice and become part of this Coastal Hazards Resilience Network that we have established here in Washington State.
Thanks, Bobek. So we have a few more minutes. We're happy to entertain questions, whether for Bobek or for me, or we'll also, if there's anything other for Crystal or for Harriet, please join in. We'd be happy to take your questions now. While we're waiting for any questions, if there's any, so there was a question. Oh, sorry, there is one a bit about the question. Let me ask actually for a clarification. Interested in hearing about SEPA. And I guess I would need a little bit more information. If somebody, whoever put the question about SEPA can put more information into the chat box, I'll answer that.
Nicole, the previous question there was, does SEPA or its implementing regulations require SLR, sea level rise data and analysis? That's the question that was referring to, yeah.
Got it, missed that one. So, Bobek, do you want to address that at all?
Sure, I think that's currently part of the conversation. I would have to defer to our SEPA team to really answer that thoroughly. So I think that's an area of exploration here, and especially with this new information and these tools available, it's something that could be a consideration.
And I would just add on to that, that whether or not it's required, and I know there's questions about, for example, for those of you who are doing shoreline master programs, are you required to address sea level rise? And the answer, as far as I can tell you, is no, it's not required. But we're trying to encourage it. And if you have a local jurisdiction that is interested in this information and using it, what we want to make sure is you understand how powerful and useful these tools are to help you get there, to be understanding how to look at sea level rise, how to look at it in the planning process, how can you make some decisions. we'll be doing more later on, talking about some more specific planning and sea level rise and adaptation measures, and how can you maybe use this information in that kind of planning process. But at this point, there is nothing that's required.
That's correct, Nicole, but I also want to reemphasize too that our shoreline planners and at Ecology are also willing to support efforts the best we can and answer any questions that come up if you are trying to integrate this information into shoreline planning or comprehensive plans.
So the question, there's another question, and this is maybe for you, Crystal, is what sort of parameters do we need to consider for sea level rise in terms of higher or lower probability?
So I'm not exactly sure what you mean by parameters, but what you want to consider in terms of using higher or low probabilities, this is really about the risk tolerance of your organization. So when you use low probability values, those are higher values of sea level rise, and that means that you are really not taking on as much risk. That the actual sea level rise that happens will exceed the values that you plan for. If you're choosing the higher probabilities, like 99, 83, those are for lower values of sea level rise. And so really in that case, you're taking on a fair amount of risk that sea level rise is actually going to be higher than the values that you plan for. So this is really that risk management connection. And what you want to consider is how much risk can you take, whether that's risk to the infrastructure, what's going to be a politically acceptable risk, how, whether or not you can revise that in the future once we actually start to see how sea level rise lines up against those different probabilities. So the fundamental thing that you're really thinking about there is what risk are you willing to take? Do you want to be more conservative, or are you willing to chance it?
So the next question is a great one, which is, do we see community members and citizen scientists using these tools? And the answer is absolutely yes. This is available for anybody and everybody. It's not designated for any one group of people to use. The issue is the question is then, how can different people use these tools? And I think that there's a lot of great examples already where communities are working on these issues and working with citizens. The marine resource committees, I know throughout the region, have done some great trainings. There's also trainings that have been going on for homeowners, for example, about how to deal with their shorelines and address erosion problems. And these are the kinds of tools that they're able to look at to deal with these issues. So there's a whole range of ways to do it. There's also, for example, Island County just recently produced a report on how to do a sea level rise adaptation process that is community-based, and the community can use all of these tools and encouraged to use all of this information in these tools for them to understand as a community, what's our risk, how are we vulnerable, how do we want to adapt, what is a plan of action that we want to take. So wide range of tools that these can be used for. So as we've talked about the site-specific, the vulnerabilities, the planning, the community-based decision-making, et cetera.
Another thing I would add there, Nicole, is that's a great question, and I would point people to the Coastal Hazards Resilience Network website. One of the resources that we've developed is a risk reduction project mapper, which provides examples of how people are solving coastal hazards problems along the coast. And for each one of those, we are developing case studies that provide lessons learned and important information to help others understand what's possible in solving similar problems across different parts of the coast.
Thanks.
And anyone is available to submit their projects to the mapper, and we can help develop those case studies as they come in.
So the website is in the chat box and then also on your screen. And so what I'm going to do is just sort of wrap us up by saying thank you for joining us and reminding everybody that this webinar was recorded. So we will be posting it both on the Shoreline Coastal Planner group website and the Churn Coastal Hazards Resilience Network website. And possibly, I believe SIG will also be putting some of it on their website. So different pieces will be available. The other thing is that we will be sending out a short survey, and tomorrow you'll all get it in your inbox. Please take just less than 5 minutes to answer it. We ask you to fill out those kinds of surveys because it helps us know how that the Shoreline Coastal Planner Group and the rest of us can serve your needs, making sure we're providing you with the information and content that you will need to do your jobs better, to continue on doing the good work you're doing. So please fill that out, help us, and we thank you again for joining us. And with that, I think I'm going to sign off and say thank you very much for joining us today. And thank you to our speakers.